Good day, students. Welcome to mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 6 to 10 of the January 2019 Algebra 2 New York Regents exam. This is going to be a step-by-step coverage of the problems. If you need a faster consideration of these questions, take a look in the link in the description below. And don't forget to subscribe and like this channel for access to the updates to this review series. Alright, let's take a look at question 6. In question 6, we are being assessed on how to calculate the compound interest when you have n times per period. Question 6 reads, Julia deposits $2,000 into a savings account that earns 4% interest per year. The exponential function that models this savings account is y equals 2,000 times 1.04 raised to the t power, where t is the time in years. Question, which equation correctly represents the amount of money in her savings account in terms of the monthly growth rate? Alright, so to do this problem, we're going to take a look at two formulas, okay? The formula for exponential growth rate when you have the time period being annually, like one time a year, and then we're going to take a look at what the formula is if it's compounded n times per year. Okay? Alright, so let's look at the formulas real quick. This is for exponential growth models. If you have once a year, the formula is going to be y equals a times 1 plus, since this growth is going to be plus, 1 plus r raised to the t. Okay? So this is once a year. Now, if it's compounded n number of times a year, the formula will be slightly different, okay? So it could be quarterly, which is 4 times a year. It could be biannually, which is twice a year, or it could be monthly, okay? Monthly, you have 12 months in a year. In this particular case, it says monthly, so we're looking at 12 times per period because we have 12 months in 1 year. So in that particular situation, we're going to be using the formula y equals a times 1 plus the interest rate over n raised to the nt. This is for a situation where it's compounded n times a year per period, n times a year. In this particular scenario, the original function, this one that's given right here, you can easily see that this formula is what is used to generate it. So let me show it to you real quick. So A is the initial amount, which is 2,000. The growth rate R is 4%. So we have to change that into decimal, which is 0.04. You move the decimal place two places to the left. Okay? And the time t is equal to t. So if you're doing it once a year, you're going to have y equals a, which is 2,000. A second. Y equals 2,000 times 1 plus 0.4, which is 1.04 raised to the t power. Alright? So we can clearly see that this exponential growth model that we have right here is consistent with the original function. Okay? But there's a slight change. We're looking at what the situation is if we have 12 times a year or for monthly. Alright? So this is annually. Now let's look at the setup for monthly, and that will be the answer to this question. So for monthly, we're going to use a different formula. We're going to use y equals a times 1 plus r over n raised to the nt. In this one, for annually, once a year, we had y equals a times 1 plus r to the t. Okay? So in this particular setup right here, let's list the knowns and unknowns. So the starting amount A is still 2,000. The rate is still the same, 4%. If you convert it to decimal, is 0.04. You move the decimal point 2 places to the left. time t is t. And then n in this case, which wasn't present before, is 12 because we have 12 times per the periods, 12 months in a year, which is a period. Okay? So if we substitute all that into the formula, we're going to have y equals 2000 times 1 plus 0.04 over 12 raised to the 12t. Okay, and if you just look at the setup we have right here, you can automatically see that the correct answer is option number 3. All right, but let me just put in the calculator, and then you can see how it simplifies. This component that's been exponentiated can be simplified using a calculator. So let's do that. We're going to have 1 plus 0.04 divided by 12. Okay, so it's 1.0033, so we can just write it to 1.0033. So it's going to be y equals 2000 times 1.0033 raised to the 12t. And we can clearly see that the answer to number 6 is option number 3. Okay, so this is basically how we use the two formats for an exponential growth model. All right, let's take a look at question 7. In question 7, we're being assessed on how to find the period of a graph, and we're looking at an application scenario where we are examining the distance between the peaks of the ocean, the peaks in the wave in an ocean. Okay, all right, so let's read number 7. It says tides are a periodic rise and fall of ocean water. On a typical day at a seaport, to predict the time of the next high tide, the most important value would have to be so we have 4 options here. So if you want to calculate the time between the high tides, okay, so you're looking at the distance between one high tide and the next high tide. Now let's go ahead and write down the component of the graph that's going to help us with this problem right here. So you want to recall what the period is. The period has a special significance when you're dealing with periodic functions. Okay, we have a periodic function here because the ocean water is oscillating between highs and lows. So what is the period? The period of the graph of a periodic function is what? Is the distance between consecutive highs and lows. The distance between consecutive highs and lows. Okay, highs and lows. Alright, so in this particular situation right here, we're looking at the time between two highs. Okay, so let's go ahead and give you a visual of what we're talking about here. So let's assume that this is the wave pattern of the ocean right here, the cycles that happen. So it goes something like this, like that. Let's put a point here, put a point here, and then put a point here. So this is the high right here, and then it goes down to the midpoint, and then it goes to the low, and then back to the center. It doesn't look good. Let's try it again. So it goes down to the low, back to the center, and then up back to the high. Alright, so the distance between consecutive highs, so this is a high right here, and this is another high. The distance between consecutive highs or consecutive lows, so let's say it keeps on going all the way here to here, that's what the period is. Okay, so if we want to calculate how long it takes between two high tides, what we're looking for is the time period between those 2 points that we have illustrated in the graph. Okay, so the distance from this point right here to this point is basically what the period is, and that's the best indicator of how much time separates the high tides. All right, so this is a period. And if you look at the options that we have, number one, it says the time between consecutive lows. Oh, so we can also use low here. So the period is going to be exactly the same. All right, so let's use the low here. So it doesn't matter if you use the high or the low, you'll still get the same final answer because they both represent the periods. Okay, so change the color here, from this low, bam, straight to this low right here, that tells you the period. Okay, so the fact that we're using lows to calculate the distance between highs shouldn't bother you because in both scenarios, the time separation is exactly the same. So if this were, let's say, 3 hours, guess what? The distance between the highs will be 3 hours also because that's the nature of periodic functions. Answer to question number 7 is option number 1 because it looks at the difference, the time between consecutive lows, which is the same thing as the distance between consecutive high tides. All right, let's take a look at question number 8. All right, let's take a look at question number 8. In question 8, we're going to be looking at how to find the intervals of increasing or decreasing of a function using our Texas Instrument calculator. All right, so question 8 reads, an estimate of a number of milligrams of the number of milligrams of a medication in the bloodstream t hours after 400 milligrams has been taken can be modeled by this function below from 0 to 6. So the question says, over what time interval does the amount of medication in the bloodstream strictly increase? All right, so what does it mean for a function to be increasing? Let's recall something real quick. So something to remember concerning the behavior of a function. A function is increasing when what? If it's going up, if it is going up from left to right. Okay, from left to right. The orientation is very important. So the function is going up from left to right, then that basically means the function is increasing. So what we're going to do is enter this function into our calculators, and then we're going to graph it and see where it's increasing. Okay. All right, so you can just enter this in your graphing calculator. You press the Y button. So let's say you have the home screen. Press the Y button, and then you enter this function into your calculator, 0.54x to the fourth plus 3.45x to the third minus 96.64x squared plus 347.7x. Okay, and then to adjust the view, you just go to the window, and we're going from 0 to 6. So for the x, I'm going to put 0 for the minimum and then the maximum y because that's the domain for the x. Okay. For the y, we're going all the way to 400 milligrams. So we can go, the y minimum is 0 and then the y maximum is 400. There's a consideration. The interval is given here. So let's go ahead and graph the function and see what it looks like. So you have something like this. All right. So you can kind of guesstimate and see that it looks like it's increasing from 0 to 2, and then it starts to decrease after that. All right. So just to confirm, you can just trace it and see what's happening. When it gets to 2, it looks like it hits the maximum point, and then after that, it starts to go back down. Okay. All right. Another thing you can do is just to find if that's where the maximum is located, and that will also help you to determine what the answer is. So I'm going to make a snapshot of the graph. So if you look at the graph right here, this is what we're looking at. This is the peak, and we can see if we trace 2, we're looking at 2 because if you look at the options that we have right here, we have from 0 to 2, 0 to 3, 2 to 6, 3 to 6. So if you look at what we're given, the best choice that we can use to indicate for where it's increasing is from around 0 to 2, slightly past 2, but considering the options that we have, we know that the function is increasing on that interval. Okay, so that interval is going up, increasing, 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 and then after that it starts to decrease. So from 0 all the way to 2, the function is increasing. Okay, increasing from 0 to 2 hours, and the answer is option number 1. Alright, let's take a look at question number 9. In question 9, we're being assessed on how to find the roots of a function, of functions presented in different formats. We have algebraic, graphical, and tabular representations. Okay, so the question 9 reads, which representation of a quadratic has imaginary roots? All right, so let's go ahead and talk about what roots are first, what real roots are first, and then we will go ahead and solve the problem. Okay, so what are the roots of a quadratic function or any function in general? So you want to remember how to find the roots. So if you're given a table, your roots are basically the x values when y is 0. In tabular format, that's how you find the roots. Okay, how to find roots. How about if you're given a graph? If you're given a graph, you find the roots by looking for the x-intercepts. At what y values does a graph intercept the x-axis? Those are the roots. Okay? I mean, what are the x values when the graph hits the x-axis? Those are the roots. And then the last one is algebraic. If you're given an equation, how do you find the roots? All you do is you set y to 0 and solve. Solve for x. Okay? All right, we have all three representations here. Option 1 is a tabular representation. So for option 1, the roots are basically where the x values are the x values when y is 0. Okay, so y is 0 here, bam, 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 and then y is 0 here also. So for option number 1, your roots are what? So for option 1, your roots are negative 0.5 and negative 2. Are these real or imaginary? Since there are no i's attached to them, they're real. Okay? Imaginary numbers always have an I component. So this is real, or these are real. Okay, option 2, we have 2 times the quantity x plus 3 squared equals 64. So this one is an equation. We have to find what the roots are for this equation. There's no y component here, so we're just basically going to solve this equation. Okay, we're going to set it to equal to 0 and solve. Okay, so to do that, we're going to multiply this out to x plus 3 times x plus 3. Well, in order to set it equal to 0, we have to subtract 64 from both sides. Okay, and then let's solve this equation. Well, let's do it a different way, a way that's much faster. So since it's set up like this, what we can do is we can divide by 2 and root it. Let's do it that way. Doing it the long way. Okay, so divide both sides by 2. So divide by 2, divide by 2. And that's going to give us x plus 3. Change the thickness here. X plus 3 quantity square equals 64 divided by 2 is 32. And then we're going to take the square root of both sides. square root, square root. And then we have, what do we have here? X plus 3. Now, if you take the square root of a square, don't forget to add on the plus or minus component, plus or minus 32. And then you subtract 3 from both sides. And then your roots for number option 2 are negative 3 plus or minus root 32. Now, since you're not taking the square root of a negative number, there are not going to be any imaginary components here. All right, so your roots for option 2, they are real. Okay, so for option 1, let me put the roots there. It was negative 0.5, comma, negative 2.0. And then for this one right here, it's going to be, and then we can simplify root 32 too. Let's just do that. It's not necessary, but it's good to know how to simplify radicals. 2 goes into 32 16 times, and then 16 can just be written as 4 times 4. And then these two 4's come out as a 4. So root 32 is basically 2 root 4. I'm sorry, it's 4 root 2. So it's 4 root 2. So the roots for option 2 are negative 3 plus, let's do the minus first, minus 4 root 2 and negative 3 plus 4 root 2. Okay, in a simplified form. The reason why I broke it down all the way is to help you see that there are no imaginary components here. Okay, for option 3, we have a graph, so we're looking for the x-intercept. Alrighty, the x-intercept here is 3, so you have the root for this one is simply 3, so your root here is just 3. Okay, that's the x value when y is 0. Y is 0 here. Okay, for option 4, we have another equation, 3x squared plus 32 equals 0. So we just solve this for x like we did the other one. So if we subtract 32 from both sides, we have 2x squared equals negative 32. And then we're going to divide by 2 and then roots, okay? All right, so divide both sides by 2. And then we have x squared equals negative 16. And then you take the square root of both sides. I hope you can automatically see that this one is going to be imaginary. Now, how do we know that it's imaginary? Well, anytime you take the square root of a negative number, you end up with imaginary roots. So in this particular case, the square root of negative 16, now this minus comes out as an I, and the square root of 16 is 4. So the roots here are plus or minus 4i. Okay, or if you want to write it in roster notation, set roster notation, negative 4i and 4i are your roots. So the problem, the function, quadratic function that has imaginary roots is option number 4. Okay. All right, let's take a look at question 10. In question 10, we're looking at how to select a good sample from a population for statistical purposes. All right, so question 10 reads, a random sample of 100 people that will best estimate the proportion of all registered voters in a district whose support improvements to the high school football field should be drawn from registered voters in the district at A. So which of these options right here will help us create the best sample for the population? So what is the guideline? What do you want to keep in mind concerning what the best sample is? Okay. Well, this is something that you want to note concerning selecting elements for a random sample. All right. So what do you want to keep in mind concerning random sampling? You want to be as unbiased as possible. All right. Whenever you're looking at a subset of the population, you want to select from an area that is as unbiased as possible. So the less biased, the less biased a sample is, the better estimator the better estimator of a population it is. Okay, so you want to try and be as unbiased as possible. So in this particular situation, we're looking for people who are in support of improvements to a high school football field. Okay, so if you look at what's going on here, we're looking at high school and football. All right, so think about the possible biases that can happen. You think about people that are in high school are going to be biased towards this event, right? Either you're in high school or you have a child in high school. Or what if you like football? If you like the game or watch the game, you'll be biased towards the supporting the improvements, right? But we want to be as unbiased as possible. So the area you want to collect your elements for your sample population from should be an area that comprised of people that are not clearly biased to either high school or football or a combination of both. Alrighty? Okay, so let's go over the options that we have here to see the population space that has the least bias in it. Okay? Alright, so for option number one, uh, people at the football game. Well, which kind of people go to the football game? Is people that care about football already have people that play the game. So this one is biased because um, you're selecting people that favor the game. All right. So let's see if there's something better. Supermarket. Well, if you take a look at supermarket, is it restricted to high schoolers or people who play football or people in high school who play football? This one is less biased, okay? It's more neutral, and that's where you want to go to get a good sample. All right, so let's just take a look at the other ones. School fundraiser. This is biased because we're taking a look at people that are in school. Okay, so people that are in a school fundraiser have a bias in favor of what you're already trying to do, so they're definitely going to be in support. And then lastly, high school band concert. What do you think about this? Does it look biased to you? Absolutely, you're selecting people that are in high school. So that automatically gives them a bias towards supporting the improvements because they are in high school and they have a favorable view of improving anything related to high school. Okay, so the least biased population area is in the supermarket, and this is the best way you can get a good random sample concerning the data you are trying to collect. Thanks so much for watching this video. Let us know what you think. If you found the contents of this tutorial helpful in your studies for the upcoming Regents exam, do give us a thumbs up. Your positive feedback is very valuable to us. If there are any questions that you'll need assistance with or any general questions concerning the Regents in general, just place it in the comment section below and we'll be more than glad to support you. Don't forget to subscribe to our channel for updates to the remainder of this review series. Tons of support resources can be found at math.serve.com under New York Regents. Thanks again for watching and have a wonderful day. Goodbye.